It's actually quite delightful to give a talk right after Tom, because he started talking about how to make encoding faster. And by meaning faster, what Tom's company is focusing is how to make it faster on a single computer, how to make it faster on a computer with multiple cores, with multiple CPUs, GPUs encoded, but this is still single system. Now, in nowadays, in our world, you don't have to run encoding on a single computer. You could run it in cloud. You can run it on thousands of computers managed by Amazon, Google, Azure, and others. But of course, the question is how to do it efficiently. And I'll talk about what it takes to orchestrate and make cloud encoding in cloud feasible, and what problems arise when you start to do that. To give a context, I bring this slide where I show what usual steps are involved in encoding. It's not only transcoding operation by itself. You also need to pull content from origin. You need to ingest, demux it, see what streams it contains, what needs to be further transcoded, what can be discarded. Then once you complete the transcoding operations, then you need to remux it. You need to mux it into final delivery format, and that will be different for different ecosystems, different delivery scenarios you envision. Some systems will prefer Dash, some systems will prefer HLS. In some cases, you might want to still keep progressive download and single file pushed on the web. It all depends on who your customers are, and there is a number of those formats. There is even more DRMs. There is even more different permutations that might happen with different languages. Also, you might want to do add insertions at the same stage, do splicing, and so on and so forth. So when we talk about mux, it's a very loaded piece of engineering that stays at that level. Then, of course, there is a manifest generation, and finally, the content is pushed to CDN. And when we talk about cloud encoding, all of this is happening in cloud, run on instances of public cloud service provider, or private cloud as well. Now, what's important also to note that some of these steps might not be static. They might happen dynamically. For example, things like manifest generation, remuxing to different format could happen on demand. You don't need to produce all permutations of all possible DRMs and encryptions and such ahead of time. It's much more practical to produce virtual space of all those permutations, and when client clicks on that link, use CDN miss as a fetch to your system to dynamically reproduce all this missing permutation and fit it to the client. So this can be done in real time, and this saves lots of resources, and primarily CDN resources. You don't need to store all of this. Now, when we talk about transcoding, there are generally two modalities. In cable world, we traditionally sent just single stream. It was encoded at some fixed bit rate. In ABR world, we of course transcode to plurality of streams, and those streams need to be rescaled, use different resolutions, use different settings that are applied to each encode, different bit rates. And of course, there are several ingredients on how to do transcoding to ABR right, which include generation of ABR ladder, figuring out how to do proper video processing, and tricks with video encoding. Now, once we think about moving things to cloud, this is really what it boils down to. If we think about performing transcoding on a single instance, and that's a model that's shown above, what needs to run on a single system is a chain of this operation, from demux to mux with transcoding in between. And this could run well on a single system, and Tom talked at length how effectively x265 and x264 do this job, but of course you need to couple them with mux, demux, and audio processing to have a full transcoding pipeline. Now, to move it to the cloud, well, In theory, it sounds like we just need to allocate a plurality of cloud instances, for example, 1,000 or as many as you could, or as many as it's practical, and allocate jobs between all those cloud instances, throwing on them mezzanines and parameters of each job as they're coming from your customers. Now, it sounds simple in theory, but there are lots of caveats. You need to think about how to distribute this work. You need to think about how to orchestrate a cloud properly, how many instances to allocate, how effectively to use it, how to distribute load between them, monitor it, ensure reliability, and minimize cost of doing this such that you don't overcharge customers and don't burn yourself as well executing all this. Now, I'll go through those steps one by one, but I think probably most interesting technical one of them is how to distribute the work across all these instances. And when we talk about cloud, we're not talking about like 10 instances or 100 instances, we're talking about thousands. It really mass scale distribution. And of course, the simplest way you could parallelize is just take each mezzanine and throw to different instance in cloud, and then as many streams that you have incoming, that's going to be your degree of parallelism. But and that actually works well. It's the simplest way to do it, but that might not be the simplest, and might not be the fastest. Even faster is to split each sequence in segments, and then throw each segment into the cloud. But if you split sequence in segments, there are lots of caveats, because one thing that happens is that you need to ensure that quality of all those encodings will be consistent across different machines that will be doing encodings. And sometimes passing just same quality parameters is not enough to make sure that that's going to be the case. Second, HRD constraints may not be met. You encode one instance without knowing what would be the fill level at the next instance, and you're going to have a mismatch. And if you catenate those sequences back together, your players may run out of decoder buffer, or if you're sending to setup boxes, the setup box might crash. So we're talking about serious problems. So there are twists on how to do it. I'll talk about this a bit later. But then there is also a third level of parallelism, which is instance level, which is each instance might have multiple cores. It might have not only CPUs, it might also have GPUs installed. And then we talk about codec level parallelism, and it's precisely what Tom was talking before, utilizing things like wavefronts, tiles, also, perhaps doing GOP level parallel encoding. So those tricks happen at instance level. Now, I'll talk a bit more on segment level encoding, because that's kind of closer to the cloud. And as I said before, HRD problem is really serious. If you just simply chop a video in 1 second intervals and encode it in parallel, you cannot concatenate it back and produce compliant stream. But the key simplification happens if you know that your delivery is not a final delivery, is not a single stream, but it is a, for example, dash or HLS with certain segments. Well, that by itself is good, because, well, if you know exactly what that segment is, then you will chop your stream in those segments, and since each segment is sent with separate SPS, PPS parameters, that resets decoder codec state, and so the problem is solved. The caveat here is that when you do transcoding for cloud, you don't know exactly what your delivery segment size will be. It could be one of many, because the segmentation is done later at max level, and the segmentation might be done on demand, depending on whichever delivery scenario it is. And for example, if it's a HLS, some people may follow Apple guidelines, use 6-second segments. Some other may use older standard, which is 10-second segment. Some might go and use 4-second segments. Now, but if you know that it is a combination of those, for example, 4, 6, and 10, then you could multiply them all, divide by greatest common divisor times to the power of number of multipliers minus 1, and that gives you the for example, in case of 4, 6, and 10 seconds, 60-second segment, which is a kind of single unit that is long enough such that when you will later chop to either of those delivery segments, your junction point will be exactly aligned to the delivery junction point during delivery. So that simplifies the problem significantly, and literally you can design the system very simple if you know that it's going to segment-based delivery system. For on-demand, it's not going to be that simple. Now, API, of course, since it's all done in cloud, you need to use cloud-based APIs to launch jobs, to get notifications back. And I will use, as an example, API of Zencoder, which is our cloud-based transcoder service. It's been in business for over 10 years, and it's the biggest product of this kind in operation. So in our case, the job is initiated just by HTTP post, and we do have a URL allocated for this. We do have several versions of APIs. Right now, the current is API v2. And what you do is in this HTTP post, you include a JSON file in the body of request, and this JSON file just says what is the input file and what is the plurality of outputs you want to produce. In this case, the input file is a MOV file and sitting somewhere in S3 bucket on Amazon, and then output specifies one output with plurality of both audio and video stream parameters, things like audio sampling rate, bit rate. For video, we specify what is the target bit rate, what is the capped for bit rate, and so on. And the number of these outputs could be many, and the system will parse this request and will automatically parallelize job and send it to the instances and produce results. Now, once job is completed, we will send notifications. So in same job create request, you could specify, for example, a HTTP address to get HTTP post once job is completed, or even email address. You could receive emails. Send emails saying that something is done. There are also error notifications. If it's not done correctly, the party that is running it will receive that type of notification. And of course, you can always log in the panel and see the what's happened, why this error occurred, and what's the status of the job, and so on. Now, going back to the problems that arise with designing the system, of course, key issues is how to allocate instances, how to distribute jobs between them, how to ensure reliability, how to manage costs. Those are the big ones. To ensure reliability, for example, we introduce redundancy. For example, there is not a single point receiving the requests. We have multiple of them. There is not a single database maintaining results. There are multiple of them because none in cloud is in stones. Every instance you instantiated might die. And you need to kind of build system to be reliable, to be able to handle all those situations. Ingest and upload techniques should be reliable. There should be retransmissions and such, and just HTTP is not the right answer in most cases. Now, in many cases, we receive mezzanines that are broken by definition, or they're very poor quality. So we use techniques to minimize that damage and still be able to complete job. Support for all sorts of legacy formats is also important if you're in a kind of mass-scale cloud transcoding business. Now, and finally, what's key, what makes encoding product better is that it has a better encoder by itself. And that includes optimization of the rate control inside of codec, and also taking care of things like pre-processing, encoder ladder design, setting right codec parameters, all those things. I'll use just 1-2 minutes out of what I have left before the coffee to talk about a few of those things. So for pre-processing, well, you receive content, and of course it is packaged in some container format, but reality of it is that container format may not necessarily contain right information about the source. You might receive progressive content encoded as interlaced, or you might receive interlaced content encoded as progressive. You might receive content with broken cadence and many other issues, and you would think that this is all legacy. Well, there are some other things that's happening. You receive nowadays, for example, the most wonderful ProRes mezzanine encoded at very high bit rate. Well, but what is ProRes? Realistically and technically, it's just a JPEG with different entropy coding. So it's as poor as JPEG in terms of blocking artifacts. And if you just give me your favorite ProRes, I'll stop you and show you frame with blocking artifacts. So if you want to do things right, you need to ingest it, you need to analyze it, you need to see what the properties are, remove artifacts that are still there, and do conversion to sampling rates and samplings that will be used for delivery. That includes temporal sampling, that includes color space, color sampling. For example, you might receive content on 444, you need to downsample it to 420, and turns out that downsampling for 444 to 420 is a black art by itself. And people who work on HDR know it in greatest details because that exposes extra problems with those processes. So those are all kind of extra know-how that each company in space develops to make sure their products are better. And finally, there is also frame rate conversion, which is also a complicated process. It needs to be done right. And so it's another piece of algorithms that is critical. Encoding, of course, when you pick up operating points, you kind of bounce between two levels. At one end, you can't encode video at a level which is so poor that it's not watchable. So I call it the lowest quality. The service is not feasible at that point. And then at the other end, you might reach to the point when you're throwing 10 megabits at 1080p stream, and you can throw 20 megabits, but you don't see the difference. So you reach a point of saturation when the quality is already so good that it doesn't make sense to waste any more bits. So the right thing is to pick points in between that are meaningful. But now how to measure quality? That's, again, a broad topic. There are a number of metrics that measure just codec noise, things like PSNR, MSC, SSM. Some of them measure things in absolute sense. PSNR measures just absolute amount of codec noise. SSM is effectively SNR, a fancy version of SNR. But none of them is exactly connected to human vision. Now, there are more advanced tools that try to model human vision and try to adapt those metrics to the different parameters of reproduction settings, and that goes to things like VPD, Visual Difference Predictor of Scott Daly, and derivatives. Tektronix has PQA, PQR metric, which is pretty decent in that sense. It's actually a Sarnoff model. SSM Wave is doing their own metric, which is derivative of SSM, but it also takes into account certain parameters of reproduction. So those are a bit better, but even none of them, I would say, is perfect. The reality of the situation is that human assessment is always a random process. Some people will look at the same image and will rank it differently. And you will also have scatter-gather plots like this. And at best, if you have an objective score, what it can tell you is what is the probability that a certain percentage of population will think that this quality is at that level. But it's not an absolute measure. So we use a combination of metrics, and we do have proprietary work in the same domain to make sure that our monitoring and our encoding is done right. Now, optimization, design of ABR ladder is another topic which is interesting, and I will probably skip details here because we have a panel later today on content adaptive encoding, which kind of naturally covers aspects of how to design ABR ladder optimally, but in a nutshell, that problem can be posed as an optimization problem with a bunch of constraints. And finally, setting right codec constraints. So the most important for streaming is to have control over the bearishness of streams. If you have two streams, one is declared as 1 megabit stream and the other is declared as 2 megabit, but 1 megabit stream at some point can jump to 4 megabits, that might confuse the hell out of your streaming clients. They might kind of start buffering, they might switch to wrong stream and so on and so forth. So to stay within stable region and make sure that majority of clients will be able to play it, you need to constrain it. And there are guidelines. Apple is recommending, initially they were recommending very narrow, like 10% variation of EBR. Now they suggest about 35%, but generally that's about the range where you should allow the variation. And what's also important is that variation range should be smaller than the steps that you have between the renditions. So you do have distinct points of operation where streaming clients can jump on. Other constraints, GOP length should be set such that you could ensure segmentation arriving at keyframes. You might also have to set them even more conservatively if you have odd insertions, and that happens, for example, on a second interval or half-second interval. Profiles level, those needs to be, of course, specified, and of course, the bit rates and resolutions should match the profile rates that you are setting. The number of reference frames, B frames, also needs to be capped because we have a number of devices that are just not going to support it. The setup boxes, the rule of thumb is that you should not go more than 4 reference frames and 3 B frames. With older iPads, iPods, it was like 2 B frames as a constraint, and so on and so forth. But luckily, in modern OTT world, you usually know which device is asking the stream. So you could actually produce several streams and then pick which one is suitable for this device. So that is the things that simplifies life in OTT. In summary, doing things in cloud is a lot of fun. There are lots of problems. I listed some of them. You could have lots of fun designing the systems that does it, or you could just try systems that exist. If you want to try Zencoder, please click on that link. If you want to try our EBR ladder design generator, please send an email. And with that, thank you. Thank you very much.